Why is it so difficult for scientists to say there are things we don't understand? They just want to pretend that it's similar to what we've seen before.
The countdown begins without sirens, without headlines, but with a jolt of urgency felt across the world's most advanced observatories. The moment Interstellar Object 3A, I-Atlas, locks into its final trajectory toward Earth, tracking rooms fall silent, then erupt into motion. Screens refresh every few seconds. Data streams tighten. This is no longer a distant curiosity drifting through space. This is a live event unfolding right now. December 19th stops being just a date. It becomes a synchronized global watch window. Across continents, telescopes pivot in near-perfect coordination. The object is still 167 million miles away, yet the level of response signals something deeper than routine science. This kind of alignment does not happen for ordinary comets. It happens when uncertainty carries weight. Quietly, without public announcement, the United Nations International Asteroid Warning Network escalates monitoring. More than 80 observatories are activated at once: professional facilities, deep space trackers, precision astrometry stations. Each is assigned overlapping roles, cross-checking the same moving target from different angles. Redundancy replaces comfort. Margin for error collapses. There is no panic in the language used. No warning is issued. But this is not business as usual. Every new positional update matters now, down to shifts measured in arc seconds, tiny angles that can mean thousands of miles at interplanetary distances. A single inconsistency could force recalculation. A single anomaly could ripple through the entire prediction chain. Astronomers race against a narrowing window. The closer 3i Atlas gets, the harder it becomes to correct errors. Models are refined hour by hour. Assumptions are stripped away. The goal is no longer discovery or classification. The goal is precision under pressure. What unsettles researchers most is not what they see, but how much coordination is required to feel confident. This level of synchronization suggests stakes that extend beyond academic interest. Something about this object, its origin, or its behavior demands collective vigilance. And as December 19th approaches, one question hangs unanswered in every control room. If this much effort is needed just to track it, what happens if it does something unexpected next? The test begins without warning. The moment 3i Atlas is officially folded into the International Asteroid Warning Network's full operational framework, the exercise stops being theoretical. This is no drill, no archived simulation, no post-event reconstruction. For the first time in human history, an interstellar object is being tracked as if it could be a threat, not because it is confirmed dangerous, but because no one can afford to assume it is not. This network did not exist when Oumuamua slipped through the solar system, detected late and gone before answers arrived. That failure still hangs over the scientific community. This time, there is no excuse. Sensors across the planet activate in sequence. Time zones blur. Observatories in different hemispheres hand off tracking duties like a relay race that cannot be dropped. The object is still far out, but the system is already under pressure. NASA-led coordination turns 3i Atlas into a live systems test. Data is streamed, corrected, reprocessed, and rechecked in near real time. New astrometry techniques, some barely out of peer review, are deployed mid-flight. This is science under stress. No simulations can account for an object that arrived from another star system, carrying unknown physical history and unpredictable behavior. The comet's trajectory is no longer just a path in space. It becomes a measuring stick for global readiness. Each observatory compares results against others thousands of miles away. Tiny disagreements emerge, fractions of arcseconds, barely visible to the public but alarming to experts. These small mismatches matter. A minor error today becomes a massive uncertainty weeks from now. Scientists know what's at stake. If the system struggles to track something visible, slow, and cooperative, it raises an uncomfortable question. What happens when the next object is faster, darker, or detected later? 3i Atlas is treated as a proxy for the unknown, a stand-in for future visitors that may not announce themselves so politely. Behind closed channels, weaknesses quietly surface. Latency delays, data formatting conflicts, regions with limited coverage create momentary blind spots. None of these failures make headlines, but they are logged, flagged, and debated with urgency. Because if tracking breaks down here, future warnings could come too late for meaningful response. This is no longer about where 3i Atlas is right now. It is about how early humanity can see the next one coming, how confident the numbers will be, how much time Earth will have to decide what to do. Every update feeds a growing realization. Planetary defense is only as strong as its weakest link. As December approaches, the system tightens, corrections pile up, and tolerance for uncertainty shrinks. The data being gathered now will shape future detection rules, response thresholds, and emergency timelines. And as confidence builds in some areas, unease grows in others because something about this object refuses to behave like past assumptions predicted. And just as the tracking network settles into rhythm, the comet itself begins to change, forcing scientists to confront a new problem they didn't plan for, setting the stage for what comes next. The warning does not come from impact alarms or fireballs in the sky. It comes from data that will not sit still. As 3i Atlas heats up, its coma swells without warning, spreading outward like a fog that refuses to hold shape. Telescopes lock on, calculations begin, and then the target changes again. The object astronomers thought they were tracking suddenly becomes something harder to define. What should be a precise point in space turns into a shifting cloud, and every second of uncertainty matters. Night after night, the comet's brightness refuses to behave. One evening it flares stronger than predicted. The next, it dims without explanation. These are not minor flickers. Each shift forces scientists to reprocess entire datasets from scratch. Gas and dust erupt unevenly, inflating the comet's apparent size and smearing the light that should reveal its true core. The nucleus, the solid heart that determines its real path, vanishes behind layers of glowing debris. Astrometry teams feel the pressure immediately. Their job depends on finding a stable center to measure from, but 3i Atlas offers none. The brightest point is no longer the most reliable one. The coma twists, stretches, and reshapes itself under solar heating, dragging measurement anchors with it. Every attempt to pin the comet down introduces a new margin of error, and small errors at this distance do not stay small. Tracking an object that refuses to hold a consistent shape becomes a nightmare scenario for planetary defense systems. Advanced telescopes can resolve fine detail, but only if the target cooperates. Here, the signal itself is unstable. Light scatters in unpredictable ways. The comet's edges blur. Algorithms designed for clean trajectories struggle as the data turns noisy and uncertain. What should be a simple arc through space becomes a moving probability cloud. That cloud matters more than most people realize. A shift of arc seconds today can translate into thousands of miles weeks from now. Predictions stretch, then fray. Confidence intervals widen. Scientists begin speaking in ranges instead of lines. Early warning models strain under the weight of too many variables changing at once. This is not panic, but it is stress, built into the system itself. The danger is not that the comet looks strange. It looks normal. Too normal. Yet its behavior quietly undermines certainty at every step. A familiar object from an unfamiliar origin, wrapped in a coma that hides its true motion, slipping just enough to keep everyone recalculating. And as December 19th draws closer, one question hangs unanswered. If the coma keeps rewriting the math, what else about 3I Atlas might refuse to stay predictable when it matters most? Something scientists are about to confront next. It should not look this normal, yet that is exactly what alarms scientists. As 3I Atlas drifts closer, its chemical readings settle into patterns astronomers know too well. Water vapor streams off the nucleus at familiar rates. Carbon dioxide signatures rise and fall exactly as expected when a comet warms under sunlight. No violent eruptions, no exotic compounds, no strange ratios. On paper, it behaves like a textbook comet from our own solar system. And that is the problem, because 3I Atlas did not form here. Its trajectory confirms it came from deep interstellar space far beyond any known planetary system. Yet its chemistry shows no scars of that journey, no alien fingerprints, no obvious warning signs. To researchers watching in real time, the data feels unsettlingly clean, too clean. An object that traveled between stars should look weathered, altered, or strange. Instead, it looks comforting, almost familiar enough to be ignored. That contradiction triggers quiet concern across observatories. If an interstellar object can mimic a local comet this well, detection protocols face a blind spot. Early warning systems are designed to flag the unusual. Brightness spikes, exotic chemistry, irregular motion. But 3I Atlas offers none of that. It blends in. It hides in plain sight. Scientists begin asking an uncomfortable question. How many objects like this have passed through unnoticed? The fear is not about this comet alone. It's about what comes next. A normal-looking interstellar body gives no early alarm, no reason to mobilize, no signal to escalate. By the time it is identified as foreign, it may already be close, too close. The most dangerous scenario is no longer a strange object, but a familiar one arriving from the wrong place. As Earth slips into the closest approach window, that realization lands hard. Telescopes keep watching, spectrometers keep confirming the same ordinary results, and behind closed doors, scientists prepare for the possibility that this perfect comet is exposing a flaw in how humanity scans the sky. Because if 3I Atlas can look this normal and still come from another star, then the next visitor might not announce itself at all. And as the countdown continues, attention shifts to the data pouring in from every direction because something about the global response itself is starting to feel just as unusual. The surge hits without warning, screens light up across continents as participation numbers spike far beyond expectations. What was planned as a controlled scientific campaign suddenly swells into something closer to an emergency response. Within days, 171 contributors are logged into the IAWN system. Professional observatories, university labs, and highly trained citizen astronomers all feeding data into the same live network. This level of engagement does not happen for routine comets. It happens when margins collapse. Mid-campaign coordination calls grow crowded and tense. More than 100 active participants join at once, some only days before the December 19th approach window. Questions flood in faster than moderators can answer them. How precise must the timing be? Which filters are acceptable? What error tolerance is allowed before data is rejected? The tone is not curiosity, it is urgency. Everyone understands that one flawed measurement could ripple across the entire prediction model. Behind the scenes, scientists quietly tighten standards. Reporting formats are updated in real time. Precision thresholds are narrowed without public explanation. The acceptable error range shrinks to levels normally reserved for mission-critical tracking. Every observer, amateur or professional, is now part of a single global calculation engine. Each data point alters the trajectory model, sometimes subtly, sometimes uncomfortably. This is no longer outreach science, it is distributed vigilance. The network behaves like a planetary watchtower, scanning the sky continuously, overlapping fields of view to eliminate blind spots. Observations are cross-checked within minutes. Anomalies are flagged instantly. Patterns that would once take weeks to notice now emerge in hours. The system is listening for something it cannot yet define. As December 19th approaches, the data volume surges again. More eyes turn upward. More signals pour in. Somewhere in that flood of numbers may be a deviation no model predicted, a shift no equation explains, and if it appears, it will not announce itself gently. Because once this many people are watching this closely, discovery stops being optional, and the next phase of the story is already beginning. Silence hits first. The moment 3i Atlas passes its closest point to Earth, alarms do not sound, headlines do not explode, and the sky does not change, but inside control rooms, tension tightens instead of fading. Screens stay lit. Data streams do not shut down. Scientists do not relax. Because everyone involved knows the most dangerous phase may begin after December 19th, not before it. The object will move away, but the questions will move closer. IADWN confirms that the campaign is not ending, it is transitioning. Observations gathered during the approach are flagged for peer-reviewed publication next year, a clear signal that explanations are still incomplete. If everything were settled, there would be no need for extended analysis. The delay itself becomes unsettling. It suggests patterns still being debated, measurements still being reconciled, and behaviors that do not fully fit existing response models. Behind closed doors, analysts replay the encounter frame by frame. They examine where predictions held and where margins quietly widened. Tiny positional uncertainties, dismissed in real time, now loom larger in hindsight. A few arc seconds here, a slight timing mismatch there. Individually harmless, together potentially revealing. 3i Atlas was never just a comet. It was a rehearsal. This was the first time humanity ran a full planetary defense coordination exercise on an interstellar object moving at real speed under real solar conditions with no rewind button. Every decision, how fast data was shared, how clearly anomalies were reported, how confidently conclusions were communicated, now becomes part of a post-event autopsy. And autopsies are where uncomfortable truths surface. What if something was filtered out too early? What if a weak signal was labeled noise because there was no category for it? What if coordination masked blind spots instead of exposing them? These are not questions asked publicly. They are asked quietly, in technical language, in closed review sessions that will shape how the next object is handled. Because there will be a next one. Interstellar visitors are no longer theoretical, they are confirmed. And now humanity knows how easily one can look ordinary while behaving just strangely enough to stress every system designed to track it. The danger is not panic, it is false confidence. The most unsettling moment may not be the flyby itself, but the calm that follows. A calm where nothing seems wrong, yet something feels unfinished. A calm where data keeps being reanalyzed because it refuses to fully settle. By the time conclusions are finalized, the sky will already be clear again, but the clock will not reset. The next interstellar object will not wait for protocols to be rewritten, papers to be published, or weaknesses to be quietly patched. It will arrive on its own timeline. And when it does, the real test will be whether humanity learned enough from the silence after December 19th, or whether that silence was the warning itself. Because whatever comes next will already be moving.